All right, so this is part two to set 19 Mountain Math. I'm going to start by going to our Google Classroom, going to classwork, and I'm going to scroll on down until I see virtual learning math. Okay, notice I'm doing something different here. We have all topics here on the left hand side. You can click and it'll send you right to it. Or this way, you can scroll on down and you can actually see the topics within the topic of virtual learning math, or at least the materials within virtual learning math. A little bit easier this way, I'm finding. And we can click on Mountain Math. And when we do so, we see that we have the first half of Mountain Math Set 19. That was numbers 1 through 8. Today is numbers 9, 10, 11, and 12. All right. So let's get started here. We will start with number 9. And number 9, we were given two numbers, 8,850 and 734, and we are to add these numbers and we are to subtract these numbers. So go ahead and start with the first part, adding the numbers. 0 plus 4 gives us 4, 5 plus 3 is 8, starting on the right-hand side of the problem and moving our way to the left. 8 plus 7 gives us 15. Carry the 1. 8 plus 1 is 9. Ones, tens, hundreds, comma, 9,584 is the sum. Now we are to subtract these numbers. This is where we want to be a lot more careful, making sure that when we are subtracting, the number along the top, the number that we're starting with, the digits are bigger than those underneath them. So we see here we have a 0. This digit 0 is not larger than the digit that is beneath it, so we will need to borrow. As I make my way across this number, just taking a look at the number before I begin subtracting, I notice that this will be the only place in the ones place that I will be borrowing to make the digit larger. So this 0 is smaller than this 4. We're going to go to the place value position to the left. That'd be the tens. And we're going to borrow 10 from these 5 tens. So when we borrow 1 10 from 5 tens, we're left with 4 tens. And if we give that 10 that we borrowed over here to that 0 becomes a 10. So now we can proceed confidently through this subtraction problem because all of our digits are now on the top. All of the digits are now larger than those beneath them. 10 minus 4 gives us 6. 4 minus 3 is 1. 8 minus 7 is 1. And 8 minus nothing, it will give us 8. Ones, tens, hundreds, comma, 8,116 is the difference that you get when you take 734 from 8,850. Okay, moving on over to number 10. Number 10 is where we are given two numbers and we are asked to multiply those numbers and we're asked to divide those numbers. Looking at our two numbers, 357 and 7, we can first multiply. The first way we can go about multiplying is the classic standard shortcut algorithm. 7 times 7 gives us 49. Put that 49 over here. Okay. That lets you know you got to do something with it. Circle it. Put the 9 down and carry the 4. Now you proceed to multiply first and then add the 4 on top. Do not add the 4 on top first and get 9 and then multiply 9 times 7. That's incorrect. Multiply first and then add the 4, which we carried on over to the tens place. 5 times 7 gives us 35, plus that additional 4 gives us 39. Put that down. Circle it. We're done with 49. We can now see a little bit easier when we put this number over here to the right hand side. We can see which digit of 39 needs to go down and which digit does need to be carried. The 9 needs to go down underneath the 5, and the 3 will be carried. Next, we multiply again first. 3 times 7. Do not add 3 plus 3 and get 6 and multiply 6 times 7. Again, that is incorrect. Multiply first. 3 times 7 gives us 21, plus 3 more. We end up at 24. Cross off the 39. We're done with it. Circle that 24. Here we are now in a situation where we can put the entire 24 down. There's nowhere else we can carry. So if we put that 24 down, we end up with ones, tens, hundreds, comma, 2,499 as our product. Another way of going about doing this is using your area models. This is where you're going to take your largest factor and you are going to decompose it. You're going to break it apart into the values of each one of those digits. The value of that 3 in the hundreds place is 300. The value of the 5 in the tens place is 50. And the value of the 7 in the ones place is 7. And then over here, you can multiply all of the expanded digits by 7. Now, this goes back to problem number 1 in Mountain Math, and that goes into the idea of what do we do when we multiply by 10, 100, or 1,000, or multiples of 10, 100, and 1,000. Well, what we did here is we simply multiplied 22,296 times 1, right? And we got 22,296, and then we added the 0. Okay, we're going to do the same exact thing, but we're not going to be multiplying by 1 over here. Rather, we are going to be multiplying by 3 first. So 7 times 3 gives us 21, and then add your 2 zeros. 7 times 5 is 35. And then add your 0 to represent multiplying not 7 times 5, but 7 times 50. Same thing here. It's not 7 times 3, it is 7 times 300, so you've got to add the appropriate zeros. And then we multiply by the value of the 7 in the ones place, which is 7. 7 times 7, a basic fact, gives us 49. Now what we do from here is we can go ahead and we can add up these digits. 2,100 or 2,100 plus 350 plus 49. And we do that, we get 9, we get 9, we get 4 and 2. Ones, tens, hundreds, comma, 2,499 again is our product. If the shortcut algorithm for you is something that is an approachable strategy, use it. If you like the organization of the area model, by all means use it. The shortcut's going to be much more efficient, but for my artists out there and those that like drawing diagrams, drawing area models, the area model strategy could be motivating for you to continue multiplying and continue practicing the skill of multiplying multiple digit numbers together. All right, so that was the first part of number 10. The second part of number 10 is to divide these numbers. Notice I'm using a piece of scratch paper here. These boxes do not provide us with the room that we need to successfully solve these problems in an organized way. So that's why you see here a piece of scratch paper being used. I'm looking at this long division problem. Remember our number 1 rule, right? If the digits in the largest place value position of your dividend, 357, is smaller than the 7, you've got to move over to the 5 so that now you are dividing 35 divided by 7. 35 divided by 7 is a basic fact. That is 5. Once you have divided, now you multiply. 7 times 5, and we get 35. You place that product of 7 times 5 underneath that which you divided, which in this case is 35, so that you can be prepared for the next step. And that next step is subtracting. 35 minus 35 is 0. Almost said 7. And after we subtract, we bring down. Bring down your 7. 7 divided by 7 is 1. 7 times 1 is 7. After we multiply, we subtract. 7 minus 7 is 0. There's nothing left to bring down. Remember, the answer here is not 0. The answer is here in 51. What you would get down here if it was not a 0 is what is remaining because your dividend would not have divided evenly into your divisor. So in this case, 357 divided by 7 gives us a quotient of 51. All right, so that is number 10 for you. Great practice there, great skills. So let me just go ahead and plug in my numbers that I received after solving. 2,499, and the quotient of, let's stick it over here, circle it, and appropriately written. I'd plug it in right there. All right, number 11. Number 11 is a problem where you are to fill in a missing number. And you're filling in this missing number because you are trying to create a balanced expression, okay? You are trying to create a balance between the left-hand side of the equal sign and the right-hand side of the equal sign. And so if you notice, look at the similarities of the right and the left, okay? We both have 156 and 156. If you were to cover those up, these sides, if you were to cover up the 78 and 100, you would notice that both sides of the equal sign are equal, 156 and 156. Now, because of this 78 and 100, it makes the right-hand side of this equal sign heavier than the left-hand side. And so this empty box is here for us to fill in with the appropriate number that will make not only the right-hand side heavier, but the left-hand side equally as heavy. So it becomes balanced, okay? You can look at the equal sign as sort of a fulcrum point or a balancing point, right? And right now, this is much, much heavier. This is pushing down. So we want to fill in this box with what number is going to make both sides of the equal sign equally as heavy. So we only have one box. Over here, we have two numbers that are making the right-hand side heavier. What can we do to take these two numbers and turn them into one? We can add them together, just as it says, 78 plus 100. Well, anything plus 100, in this case, you're just going to be filling in the ones place and the tens place with the 8 and the 7 respectfully. So you end up with a number of 178 that will balance the left-hand side and the right-hand side of the equal sign. So fill in the missing number. That missing number in this case was 178. Those are great problems. All right, so let me back up. Number 9 or 10 can be used here to create a story about either one of these scenarios. The scenarios would be the numbers that are involved in the problems. All right, so let's look at the doozy at which we call number 12. Number 12 is, again, it actually has its own tutorial video in our Google Classroom under Virtual Learning Math. But for today, we will go ahead and use set 19 as another chance for us to work number 12 together. What I'm going to do is I'm going to take a look at my set 19 paper that I got in my work packet, and I am going to plug these numbers in. I could also access set 19 and its numbers within Google Classroom under Mountain Math and Virtual Learning Math. 10/20ths and 7/10ths are the two numbers that we will be working with in number 12 today. And in my opinion, these numbers are friendly. They are going to be a bit more friendly to work with as we try to figure out, are they equal or are they not equal, and then eventually making them equivalent. 10/20ths and 7/10ths. Okay. What we want to do first is figure out, are these fractions equivalent? Now, there's a couple of ways to go about this. The mental math way is to look at your numerator and compare it to your denominator. Is your numerator more than half of 20? So if you took 20 and divided it by 2, would that number be 10? Would it be less than 10 or greater than 10? And that will let you know if your fraction is less than or equal to or greater than 1/2. That is a great mental math strategy for thinking about fractions. 1/2 is considered a benchmark fraction, a fraction that we can visualize, we use a lot in our daily life, whether we're speaking or cooking in the kitchen, or we are measuring out boards to be cut in a wood shop or construction site. We can look at these numbers and compare them to 1/2 to figure out, are they equivalent? Now, 10 is half of 20. 10/20ths is equal to 1/2. Another way to determine that is if there's a 0 on top and a 0 on bottom, you can cross those zeros out. They can cancel each other out to create a smaller fraction. In this case, we created 1/2. Now let's look at 7/10ths. 7/10ths is, well, ask yourself, is 7 half of 10? 10 divided by 2 gives you 5, right? So if 10 divided by 2 gives you 5, your top number is greater than 5. That makes 7/10ths greater than 1/2, right? So what we can do now is look at our original fractions, 10/20ths and 7/10ths, and we can determine which one is larger, and we can determine immediately that these fractions are not equivalent. No, they are not equivalent because 7/10ths is greater than 1/2 and 10/20ths we noticed was equal to 1/2, right? So that is the first part of, or the first way to go ahead and determine if fractions are equivalent. Another way to find out if fractions are equivalent is to put both of the fractions into simplest form. Simplest form means that you are going to find the greatest common factor between the numerator and denominator of both of the fractions. The factors of 10 are 1, 2, 5, and 10. The factors of 20 are 1, 2, 4, 5, 10, and 20. The greatest common factor, well, we have common factor here, here, and 10. 10 is the greatest common factor, and because Mountain Math is creating a good routine of us of recognizing that greatest common factor, put a square around it, and now we can divide the 10 and the 20 by 10 to get 10/20ths in simplest form. We got 10 divided by 10, that equals 1, and 20 divided by 10 equals 2. So you can see now why we were able to simply cancel out these zeros and get to 1/2. But for these purposes, we now put 10/20 into simplest form, which is 1/2. Now let's see, what are the greatest common factors of 1 and 7? Well, the factors of 1 and of 7 are simply 1 and 7. And again, the factors of 10 are 1, 2, 5, and 10. The only common factor is 1, which also makes it the greatest common factor. And if we divide 7 by 1 and 10 by 1, we end up with the same exact fraction, 7/10. 7/10 is 7/10 in simplest form. Why do we put it in simplest form? We put it in simplest form so we can get that denominator that's 12 or smaller. Why do we want the denominator that's 12 or smaller? So that we can use our fraction strips to compare the fractions, of course. So we have 1/2 right here, okay? And then we have, so there's our 1/2 mark, right? All that. And then we come down to 7/10, 1/10, 2/10, 3/10, 4/10, 5/10, 6/10, and 7/10. So here's 7/10, here's 1/2, and again we can see that 7/10 is a bigger piece of the whole than is 1/2. Okay, 7/10 is greater than 1/2. That's why we put it in simplest form. Get your fractions in simplest form so that you can get a denominator 12 or smaller, so you can use your fraction strips to do your comparing. So 1/2 or 7/10 is greater than 1/2, right? So that is the first part. Are the fractions equivalent? No, they are not. The way that they are lined up, 1/2 we found, or 10/20 we found, is smaller than 7/10. So 10/20 is less than 7/10. Here I just wrote it the opposite and said that 7/10 was greater than 1/2. Okay, same meaning, just different order. And now we have to follow our command with, if not, make them equivalent. And this is where Mountain Math problem number 5, locating the least common multiple, will help us. To make these fractions equivalent, let's start by getting the denominators to be the same. So we have a denominator of 20, and we have a denominator of 10. Now, what we want to do is find the LCM, the least common multiple, the smallest multiple that these two denominators have in common, so that we can divide by them. So that we can not divide by them, so that we can create a denominator that is the same for both fractions. So we have the denominator 20, the multiples are 20, 40, and let's just stop at 60, because I anticipate the smallest common multiple is going to be 20, as 20 is a multiple of 10, and it's the first one for 20. We have 10, 20, 30, 40, 50, 60, and we could keep going and going and going. We see that 60 is a common multiple, but that would be the greatest common multiple. 40 is a common multiple, but it is not the least common multiple. And we have a common multiple of 20. 20 is the least common multiple, as I attempt to follow Mountain Math's instructions and put a star around the least common multiple of 10 and 20. So now we can begin to think about, what is our new denominator going to be? Our new denominator is going to be 20. That's why we find the least common multiple. The least common multiple is the new denominator. Now we just have to figure out, how did we make 20 from each one of these denominators so that we can change the numerators appropriately? So we started off with 20. Now, how did we make 20 from 20? We multiplied by 1, right, to get 20. What did we, well, if we do that to the bottom, we have to do that same thing to the top. So 1 times our numerator, 10, gives us 10 again. So our denominator didn't change for 10/20ths, so therefore our numerator did not change either. For the denominator of 10, it's a bit opposite, okay, or it's a bit different, because we had to do something to 10 to make 20. What did we have to do to 10 to make 20? We multiplied 10 times 2 to make 20. Now, whatever we do to the bottom, we have to do to the top. So if we multiplied 10 times 2 and got 20, we've got to multiply 7 times 2, which will give us 14. So our two new fractions, or our two fractions that we are going to play with in order to make these two 10/20ths and 7/10ths equivalents, is 10/20ths and 14/20ths. Here we have some options. Here we can add 4/20ths to make, add 4/20ths to make 14/20ths. They are now equal. Or we could subtract 4/20ths and get 10/20ths, which would make them equivalent as well. So at this point, your goal is to choose. Do you want to add to one fraction, or do you want to take away from another fraction in order to make them equivalent? Here, if they are to be equivalent, your choices are 14/20ths. That's because you added an extra 4/20ths to make 10/20ths, 14/20ths. Or it could be 10/20ths, and you can get 10/20ths by subtracting 4/20ths from 14/20ths. Okay, so those are your two options. Now, the final step, right? The final step here is to put every fraction answer into simplest form. So the easiest way of going about doing that in this case is, if you chose 10/20ths as your answer, you've already put that in simplest form, and that is equal to 1/2, because 10 is half of 20. Or you can take 14/20ths and put it into simplest form. How do you do that? The greatest common factor. So the GCF, or greatest common factor, is used to put fractions into simplest form. So 14/20ths, list the factors: 1, 2, 7, 14, 1, 2, 4, 5, 10, and 20. Now you've listed your factors. What is the greatest common factor of these two? Well, I see a common factor here and here for 1, and 2 is common, and those are our only common factors of 14 and 20. So we can now divide 14/20ths, or 14/20ths divided by 2. 14 divided by 2 gives us 7. And 20 divided by 2 gives us 10. So our final answer here in simplest form of 14/20ths would be 7/10. Okay? Simplest form. 1/2 is the simplest form of 10/20ths. All right. Drawing pictures, I'm going to leave that to you. Drawing pictures is just like drawing your fraction strips for yourselves, or drawing anything that is broken up into 10 parts or 20 parts. Add them or subtract them if you can. When we are adding them, we are going to be adding the fractions that we changed, okay? Or the fractions that we made when we made them equivalent. So what we want to do is we want to add, well, I'm choosing 10/20ths as my final answer. So I'm going to add 10/20ths, okay, plus 10/20ths. When you're adding fractions, make sure that your denominators are the same. It makes your life a lot easier. Next week, we will be experiencing adding and subtracting fractions with like denominators, and we end up with 20/20ths or 1/2. If you have all of the parts 20 out of 20, you have 1/2. 1/2. All right. And if you were to have chosen 14/20ths, okay, you would do the same thing. You would add 14/20ths plus 10/20ths, okay? So however you want to do it, I chose 10/20ths and got 20 over 20 or 1. All right, that is number 12. So set 19, Mountain Math, that is a wrap. Make sure that you're stopping and starting these videos. If you haven't started doing that yet, start doing it now. That way you can allow your neurons to build connections within your brain, creating strength when it comes to problem solving. Take care.